Did you hear about the statistician who took the Dale Carnegie Secret of Success course? He improved his confidence from 95% to 99%. And we will be talking about how confident we feel about our intervals. So first of all, let's talk about standard deviation, which was primarily what we've been using all along. It is the ruler for statistics, and it's calculated where the model shows the model centered at p, the true proportion, with the standard deviation where I take the true proportion times q divided by n. But we rarely know p. So that means we actually rarely know the standard deviation. It really doesn't change how you're calculating anything. It just changes what we call it. Now we're going to use what's called the standard error because we're going to use our sample values for p and q to determine the theoretical standard error. So one thing we're going to look at is where will p hat actually be on the distribution. Remember, the population parameter for the proportion, p, never changes. So p is something that is just kind of like truth, all right? And p hat is a statistic we measure from our sample, all right? We don't know the actual location of the true portion p, but its location never changes. So when we are taking measurements here, we're estimating where p is. So let's go ahead and look at a simulation. On this graph here shows the normal distribution. Here is the center for the true proportion. Right now we're going to say, we're just going to center it at 0. And all I'm worried about is how many standard deviations I am away from this true proportion. So I can mimic taking a sample, because remember, normally we don't know the true proportion. So we're going to estimate it by taking a sample. So I take my sample here, and it's 1.5 standard deviations from the mean. All right, so that means if I were to use this sample, then I would draw my distribution centered around that. Okay, for this point, it looks like I have a pretty good shot of capturing. I've landed pretty close to the true proportion. But is that always going to be the case? Well, it looks like most of the time I'm going to be landing about 2 standard deviations from the mean. Let's take a look at our points here. So far, all of them, what's that? That one's negative 2.4 standard deviations from the mean. Can that happen? Of course. So you're not guaranteed. Normally we like to use about 2 standard deviations or whatever we set, but you're not guaranteed your confidence level that you're going to land where you're hoping to land. Just by the very nature of taking samples. And as I keep taking more samples, I got another one further away. Negative 2.5 standard deviations away from the mean. So you can see that occasionally, if I had used these points for my mean, and there's no reason for me not to because I don't know about all this other stuff going on, I don't know the actual true proportion value, my curve would actually be drawn all the way over there. And if I add a bunch of more points, you can see I could have curves centered here, or it could slide all the way up here. So there's a big range for where I could be hunting for the true proportion. Now, by the way, the true proportion doesn't move, and we should never say that it does. What we're saying is, what is the probabilities that, or what is the confidence that we have that we captured the true proportion within the range we specified? So we're never going to know where we're landing on this graph right here. So how confident do we want to be? We could always set a window that includes the entire range of outcomes, right? And I like this Garfield cartoon in your book. Taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. And Garfield says, this guy's never wrong. And we can go with that option. But how useful is that? It really means we don't know anything, all right? So what we could do is use the standard deviation. Remember, that's our measuring stick for statistics. And what we could do is try and look at different standard deviations or different numbers of standard deviations. As I mentioned before, if I wanted to be 100% confident of capturing what the true population proportion is, I could just set the window for all possible values. Now here I just have it from -4 to +4 standard deviations, and that would work. The problem is, as you saw in the cartoon, how useful is that? Well, another thing I could do is just try and remember that standard deviation is the measuring stick for statistics. So I could say, well, let me just set 3 standard deviations. And you may recall from our 68, 95, 99.7% rule, this would be 99.7% of the data. This can still be pretty broad depending on what you're working with. A lot of times people would go with just the 2 standard deviations, which is just a touch over, for some reason, there we go, 95%. So in fact, well, I'll get to what the actual 95% value is. Okay, actually, I'll tell you right now. The 95% value, if you just bring it in just a touch, 1.96, and that's typically what we use for 95%. It's not exactly 2, but 1.96 standard deviations. All right. We could, now the advantage of this is now my window is starting to get a little smaller, and I still have a pretty high confidence of 95%. I could keep bringing these values in. I think it's about that much, and try to just give up a little bit of confidence. So like, let's say I came in 1.5 standard deviations. That's probably a little more normal thing to do. And you could see I'd have about an 88% confidence if I used 1.5 standard deviations. If I used only 1 standard deviation, which would say, hey, you know, this is the window I'm trying to use to capture, the only problem is that my confidence level drops to only 68% for that. So now remember, we don't actually have standard deviations for our data. We have standard error instead because we don't know the true population parameters. So however big, however we want our confidence level, that determines our multiplier. And these are the multipliers right here. However many standard deviations we set for the window, or standard errors, I should really say, since we're basing our confidence intervals on our statistics instead of the actual population parameters. Now, the other thing is we call each half of our window. So if I go centered at 0 here and then go to the left, that's what we call the margin of error. So each half of this window, however big it is, that is our margin of error. And normally we will write our confidence interval as estimate plus or minus our margin of error. We can also actually do it with parentheses and then this lower level, whatever it is in actual life, and then comma, this upper level, and then close parentheses. That's another way to list a confidence interval. So let's go ahead and take a look at critical values and margin of error. So how are we calculating the margin of error? Again, we already said that we are going to figure out how many standard deviations away or standard errors away from our sample mean or sample proportion that we're going to use. So this is Z star, which is a lot like Z score, all right? And it's called the critical value. We can find a critical value for any confidence level by determining the Z star that captures approximately that percent of the data. So here are some more exact critical Z values for different confidence levels. If I want 90%, I'll use 1.645 and negative 1.645, and you can see it here. For 95%, I'll use 1.96 instead of 2. So remember, when you're doing 95%, that's pretty common. You might want to remember these. By the way, this formula is not on your math chart, so this is something you have to memorize. So what does 95% confidence really mean? Well, our intervals have the form our estimate plus our margin of error. So here's a bunch of different intervals. So let's say we had a whole class of students do a sample, and the red dot is the mean of each of their samples, the proportion they got. then their margin of error, basically they took their standard error and they would have multiplied it by 1.95 to do the high value and the low value. And so if I were to plot all of these different results here, you can see that some of the students would not have actually captured the true proportion in their interval. This person missed it. This person has it in their interval. So does that one and that one and that one. Here's another miss. So occasionally what it means when you have a 95% confidence, and I'm not saying this is a 95% confidence interval, but it's some confidence interval. When you have a 95% confidence interval, that means that you're going 95% of the time, we're going to capture the population parameter, or in this case, a true proportion, in our 95% confidence interval. So 95% of these little intervals should capture the true population parameter. And remember, our confidence is in the process of constructing the interval, not in any one interval. So how do we choose, what kind of confidence levels we want? You probably think, well, I want to be really confident. I want to have a very high confidence level. That's great. You're more likely to capture the population parameter P. But the problem is you're going to have a bigger margin of error because you're going to have to set a bigger window, 3 standard deviations. You'll have very high confidence. You just won't be able to say, you can't set a very small, you're less precise. Let's put it that way. Let's say you're willing to deal with a lower confidence level. That means you're less likely to capture P, but you're more precise because you have a smaller window. Now, most commonly, the confidence levels we use are 90, 95%, and 99%. All right. And we go ahead and rewrite this. This is really called the 1 proportion Z interval, and that's what it's referred to on your calculator. So it's going to be in the format that you have your sample statistic here, plus or minus your critical value times the standard error for your sample, right? And again, the critical value depends on the particular confidence level that you specify. Now, just like before in statistics, before we start doing any calculation, we really need to be in the habit of checking our assumptions and conditions. So first of all, there's the independence assumption. That is, data values are assumed to be independent from each other, and we can check 3 conditions. Is it plausible that they're independent? Is there any reason to believe that the data values somehow affect each other? Was there randomization for the sample? Is the sample size no more than 10% of the population? So you still want to check these assumptions here, all right? There's also the sample size assumption. The sample needs to be large enough to be able to use the central limit theorem. And we need at least, this is a success-failure condition, we must expect at least 10 successes and at least 10 failures, where NP is greater than or equal to 10 and NQ is greater than or equal to 10. So let's go ahead and take a look at an example. We've got a school budget and the local paper is polling a random sample of 330 voters. They find that 144 say they will vote yes on the upcoming school budget. So if we want to create a confidence interval of who's going to vote yes on the budget, how do we do that? So they want us to just use 2 standard deviations and concentrate on the conditions and interpretation. So let's focus, because that is always how we should be starting our problems. Conditions and assumptions. So first of all, plausible independence. It is reasonable to think the responses were mutually independent, provided, and you might need to be saying this, provided that good surveying techniques were used, all right? Because they could have polled in some location that introduced bias. We don't know. They do say it's a random sample of 330 voters. So that meets the random sampling condition. The voters were sampled randomly. 10% condition, provided there are more than 3,300 eligible voters, 330 is less than 10% of the population of voters. Now, if this was Cedar Ridge and we were polling students, this is actually greater than 10% of our population, and we would have had an issue right there. Finally, looking at success failure, well, I could do N times P, but I already know what my success is. They found 144 yeses. And then the rest were failures, so I have 186 failures. When you're calculating NP and NQ, or your successes and failures, you should always be showing the actual numbers. Never just say, oh, it needs to be greater than or equal to 10. They want to see that you know how to calculate it. So since the conditions are satisfied, we can use the normal model to find a 1 proportion z interval. All right. Now we have to be careful how we describe the interval. Don't suggest that the parameter varies. So for example, a statement like there is a 95% chance that the true proportion is between two numbers. All right. What that implies is you think the parameter can move around. So don't say there's a chance that the parameter is. Okay. Don't claim that other samples will agree with yours. So if you said in 95% of samples of U.S. adults, the proportion who think, this is from your book, marijuana should be decriminalized will be between this percent and that percent. The interval isn't about sample proportions, but about the population proportion. All right. Don't be certain about the parameter. So saying between this percent and that percent are whatever you're measuring, that doesn't work either. That's too much certainty. Don't forget, it's the parameter that we're trying to capture, not the statistic. We actually are 100% sure in the previous example that the proportion of people who responded yes is 144 out of 330. All right. We don't have to say, oh, there's a percent chance that the sample is between these two. No, we actually have the data. Okay. Don't claim to know too much. Don't say, oh, I'm 95% confident that between this percent and that percent will behave whatever you were measuring. Okay. But do take responsibility. So say, you are welcome to say that there's some uncertainty, and you should use hedging words, as I've said before. You can say that we sampled, I sampled, that sort of thing, and that's okay. So we're going to go back to our school budget and determine our confidence interval since we discovered that we could meet the conditions, all right? So we have our p hat, which is basically the fraction of yes votes, 0.436 or 0.436 thousandths, if I say it more properly. I'm going to go ahead and calculate the standard error, okay, basically using the standard deviation formula, all right? Here's the standard error formula. Not on your math chart, so you have to know that this is standard error when you're using sample data. So I plug in the numbers. 0.436 times 0.564 divided by 330 is a roughly 27 thousandths. Now I'm going to find my margin of error. So what kind of confidence did they say? Well, they told us go ahead and just use 2 standard deviations. And 2 is a really great number to use. If it's not too wide, 3 is even better. All right. Depends on how wide you want your statement to be. All right. And so we calculate it and we get 0.054. So that means I can say the confidence interval is my proportion plus or minus 0.054. So every one of these number of standard errors goes up by roughly 0.03, so or 3% for our little survey, which means if you're okay being off by almost 10% either side, you could go to a 99.7% confidence interval. But most people want to be a little closer than that. Here they're saying roughly 0.436 plus or minus 0.054. So how do we word this so we don't say too much or too little? We are approximately 95% confident that between 38.3 and 49.0% of voters will vote yes on the upcoming budget. This would be an acceptable sentence. The weird thing here is they do have approximately, and the reason they do that is we use 2 standard deviations. 95% confidence is actually 1.96 standard deviations or standard errors, okay? Notice how it takes responsibility there. There's our confidence. And then we give our range, okay? Now, your calculator does this as well. So press Stat and go to Test, all right? So I'll go ahead and turn on my calculator, pressing Stat, going to Test. And then I'm going to scroll to A1Z prop, which is about A on the list for most of the calculators. And then when you enter it, you get this sort of level here. You've got to put in X, which is the count that meets the criteria, 144 for our example. Our sample size was 330, and we did a 95% confidence level. So the nice part here is you don't have to remember that 1.96 is the Z value. And then it'll basically give you that report right there, where here's the lower level of your confidence interval, and there's your higher level, which is pretty close to the numbers we were using. Oh, and yeah, it's confidence level will be a decimal, so 95%, it should be in 0.95 instead of 95%. So let's take a look at another example. For a new medication, an experiment finds that 27% of 53 subjects report improvement after using a new medicine. Create a 95% confidence interval for the actual cure rate. And we're going to use Z equals 1.96 because we're trying to be a little more exact. Our critical value is 1.96. First of all, what's the first step? Conditions. Plausible independence. One patient's response to the medication should not influence the other patient's response. Hopefully, they also use placebos just to get rid of that effect. Random sampling condition. Hopefully, the experiment included random assignment of volunteers to treatment groups, and honestly, hopefully those treatment groups included a placebo. 10% condition. The 10% condition does not apply. We are testing medication, not patients. So we don't have to, and even if we were worried about it, this would definitely fall less than 10%. Success failure. So people who respond to the medication and people who don't. We've got N times P hat is 14 here in this part for success, and we've got 39 failures. So we exceed 10 for both, and we meet the success failure criteria. Condition. So the conditions are satisfied, so we can use the normal model to find a one proportion Z interval. So let's go ahead and calculate it. With P hat, we know is 0.27, and N is 53 based on the problem. We're going to go ahead and calculate our standard error, and we get 61 thousandths. Let's go ahead and find our margin of error. We're going to use 1.96 for our critical value here, all right? And we've already calculated that. So our margin of error is going to be 0.12. So our confidence interval is going to be this mean, 0.27, plus or minus 0.12, or basically 0.15 to 0.39. Here's how we write the sentence. We are 95% confident that between 15% and 39% of people will improve after using the new medication. Now, it might feel a little strong because it's using the word will, but since we're doing the confidence, that kind of puts a nice hedge on it. Okay, so why is this interval so wide? The interval is wide because the sample size of 53 doesn't provide a great deal of accuracy. The standard error is still pretty big in comparison to the proportion we're looking at. And since we're using a 95% confidence level, we're giving it precision. So maybe we should go ahead and make it narrower. What are the advantages and disadvantages? So let's go ahead and do the calculations. The same standard error, so I don't have to recalculate that. Now instead of what were we using, 2 or 1.96, now we're going to use 1.645 for the 90% confidence level. And we get 0.10 as the margin of error. So now we can say the confidence interval is 27 hundredths plus or minus 10 hundredths, or basically 17 to 37 hundredths. Our statement would then be reworded to say we are 90% confident that between 17% and 37% of people will improve after using the new medication. Now, this does have the advantage of being more precise, but you'll notice we had to lower our confidence from 95% to 90%. So there's always going to be this give and take. How confident are we we're going to capture the true proportion? But how big a window do we want to say? Usually in the papers, you want as small a window as possible.